So welcome to MIT InnoTherm. This is a Colloquia number 12. I'm Gang Chen, and we have the rest of our organizers here. And we usually in the past hold this colloquia on Wednesday, but this semester, since pretty much every of us have a conflict on Wednesday, we changed it onto Tuesday. So today is the actual first day they're using Tuesday for this colloquial series. So today we have a really a topic that everybody cares, personal thermal comfort. And then we have a very exciting perspective from three distinguished researchers in this field. I'll leave the introduction to our moderator, Sweta Boriskina. I will introduce Sweta and hand over to her. So Sweta is currently a research scientist at MIT. She's the lead editor of Energy and Environmental Optics Express. And she served in the past the director of Optical Society of America. And she was a research associate at Boston University and senior research scientist at Kharkiv National University. Her research areas are in photonics, plasmonics, and metamaterials, textile engineering, biochemical sensing and spectroscopy, energy conversion and transport, nanoscale transfer, heat transfer materials and devices. And then now that in the past semester, summer, she actually had a course on fashion engineering. So with that, I'll turn over to Sweta. You can take over. I'll stop sharing and go to background.
Thank you very much, Gang. And I will switch to sharing my screen. Okay, it's a great pleasure to moderate this panel of very distinguished researchers who worked in the field of personal thermal comfort from different aspects for a long time. So our first speaker will be Professor Tufan from Hong Kong, currently from Hong Kong Polytechnic University. So his research spans decades, and he has a lot of expertise in fiber science and apparel engineering. He previously worked at Cornell University at the Department of Fiber Science and Apparel Design there. He used to be president of the Fiber Society and fellow of Royal Society of Arts, among other honors and degrees. And his research areas span heat and mass transfer through fibrous materials, thermoregulatory textiles and clothing, and body beauty and fashion aesthetics. Then our next speaker would be Professor Yi Tsui from Stanford University. So his research is also quite broad and covers battery research and engineering, in addition to thermal management in textiles and fabrics and other materials. So he holds a lot of awards in the field, including ECS Battery Technology Award. He is a fellow of multiple international scientific societies. And he was named among top 100 Young Investigator Award recipients. So his research areas again span batteries, solar cells, electrocatalysis, wearables, and environmental technology. And our third panelist today will be Professor Renkun Chen from UC San Diego, from the Department of Mechanical and Aerospace Engineering there, and Material Science and Engineering program. So he brings expertise also in micro and nanoscale heat transfer, thermoelectric materials and devices, and solar thermal energy conversion. So among these three panelists, we will cover a lot of topics which are very important for personal thermal management in textiles. So just to remind everybody, and for those of you who joined for the first time, the general format of this event is we will have presentations for about 40-45 minutes. Then we will have a joint discussion for about 30 minutes. So you are encouraged to ask questions as the panelists speak through the Q&A button in Zoom. And we will be taking questions from that stream and asking them aloud. These questions will not be visible to other attendees. So if you would like to stay anonymous, you can stay anonymous. And please also help us to plan future sessions by submitting suggestions, any suggestions that you might have for future topics or speakers you would like to see on this panel. Just to remind you that this colloquium is being recorded and it will be later posted on YouTube so you can watch it. And this might include questions that we will not get time to answer today if that happens. And again, if you'd like to stay anonymous, you have a right to do so. And so before I pass it over to our panelists, I just would like to remind everybody that this is, again, this is a topic very important. We all need clothes, and in many cases, people don't think about clothes design or textile engineering as something very novel because they've been around with us for millennia. But people keep thinking of new designs and new opportunities to cool or heat by using clothes that we have to wear anyway. And I just want to show with you on this, share with you on the screen a couple of designs for the fashions of the future that were presented in 1939 by the Vogue magazine. And two of the designs had to do with thermal regulation. One on the left provided an idea for passive thermal regulation, and the one on the right an idea for an active thermal regulation. And guess what? We're in the future now. So what was the future in 1939? We're here, and we do have actual working designs that provide both passive and active cooling and heating. And this is something that our panelists are going to talk about today. So I will stop sharing, and I will pass it over to our first speaker, Zhang Tufan.
Okay. Let me share my screen. Sorry, let me go from the beginning. Okay. Hey, why? Excuse me. Okay. So good morning and good afternoon or good evening, depending where you are. I feel honored to be invited by Professor Zhang to share our work and also have this opportunity to discuss with the professors from MIT, Stanford, and UC San Diego, and many of the researchers online about the personal thermal comfort and the challenges we have in the textile and clothing, and to meet this expectation that also affects every one of us. Now, because we are now tonight, for me night from Hong Kong, because today we are with perhaps the best brain of this planet, professors and researchers from MIT, Stanford, and so on. So to start with my presentation, I want to make a big claim and just to steer some discussion, right? So what I want to claim is clothing is actually the first invention of mankind. Okay, this is according to the Bible. Because as soon as a human's eye opened, and Adam and Eve's eye was open after eating the fruit of the knowledge, and they realized they are naked, and they actually take off the fig leaves, sew them together to cover themselves. And this is perhaps the first piece of clothing mankind made. But interestingly, at least according to the Bible, that first piece of clothing was not made for thermal reasons, but rather it was made for psychological reasons, because they feel ashamed of their body, seeing them naked. So one possibility, is perhaps when God made the thermal environment in the Garden of Eden, the thermal environment was perfect. We don't really need clothing to wear at that time. So what kind of environment that would be? Now a person standing with a light activity, he generates about 70 watts per square meter metabolic heat. And for an average person, the surface area of the body is about 1.6 square meter. So we talk about 110 watts of metabolic heat a person can generate when he's standing. And about 10 watts perhaps is dissipated through insensible perspiration or respiration. So we talk about 100 watts need to be dissipated by conduction, convection, and radiation. We call the dry heat loss. And if it's on the no wind condition, to keep our body temperature comfortable, the environment temperature would be about 29 degrees Celsius if it's without wearing anything. Now, human, when it's exposed to hot or cold condition, human has some ability to regulate its temperature by, we call the human body's thermal regulation. Initially, perhaps through the vasodilation, if it's feeling hot. So basically, it's pumping more blood to the skin surface, increasing skin temperature, so increase the heat dissipation. Now, if the temperature getting higher, or metabolic rate get even higher, cannot sufficiently dissipate the heat, then we, as a human, will sweat. And sweat will generate evaporative cooling. Right? In the cold condition, to reduce the heat loss, one would have vasoconstriction, which means to reduce the blood flow to the skin and reduce the skin temperature, and therefore reduce the heat loss. But in the extremely cold condition, then a person may be shivering. Okay. So without clothing, we can only live in a very, very limited environment. Now, not only I think we need clothing for survival, but in terms of our human performance, we want our human body to stay in a thermal comfortable condition. Now, what is a thermal comfort? According to Ashley's definition, this is the condition of mind expresses satisfaction with the thermal environment. So it's basically a psychological expression. Comfort is a psychological expression, but is directly linked to the physiological condition. The physiological condition can be quantified in terms of the core temperature, which should be between 36.6 to 37.1. Now you can see that for a male person, the skin temperature should be between 33 to 34.5. I mean, in terms of mean skin temperature. and local area temperature could be lower or higher. But for females, that range can be a little bit bigger, from 32.5 to 35 degrees Celsius. Now, to stay comfortable, there's another requirement, that is no sweating and no shivering. And skin must be dry with insensible perspiration, about 15 to 22 grams per hour. And to keep comfortable, actually it's a question of heat balance. That means the metabolic heat generated needs to be dissipated by conduction, radiation, evaporative heat loss, or respiration. And in this equation, the S represents the heat storage. So in the thermal comfort state, S should be 0. But the metabolic rate actually changes very widely. When we are sleeping, it's about 30 watts per square meter, which is about 45 to 50 watts. Now, when we are resting in the sitting condition, it's about 58 watts per square meter. But when it's in very active sports, it can increase to 600 watts per square meter. So this is about 1,000 watts, basically. Now, to keep warm in a cold condition, it's relatively easy. You can just wear more clothing, but the challenge is to have a lightweight clothing while still keeping our body warm, and also breathable, because if you wear too much, clothing will be heavy, bulky, and blocking our perspiration get dissipated, which will create a wet skin, extremely uncomfortable. Now, for cooling in the summer, or when a person is in active sports, this is actually much more challenging, because you can wear less, okay, but you have to wear minimum, but you might still not be able to dissipate sufficient heat. So the only way is to have a perspiration and evaporative cooling. So if we look at the various kind of clothing for thermoregulation, I would classify it into two groups. One is passive thermoregulative clothing. Another is active thermoregulatory clothing. By passive means it assists human thermoregulation through the properties of the clothing materials or responsiveness of the materials. By active means there's external active control in either changing the property of the clothing or assisting the heat dissipation or providing heat to the clothing system. So I would like to firstly share, some of the basic properties of common fibers like cotton, polyester. We all have experience, like wool. One thing perhaps people tend to ignore or neglect is that actually many of the common fibers we're so familiar with, they are actually thermoregulatory and responsive, or we call the smart fibers. Like wool fiber is actually a very smart fiber, because as the fiber absorbs moisture, which could be from our human body, or could be as when we walk from a relatively dry condition to the humid condition, it absorbs moisture, it will release a lot of heat. Okay, but this is transient in a short period of time. Like in this graph shows perhaps within like 5 minutes, the effective insulation can increase because the wool release the heat. But like polyester or nylon, they are non-absorbent fiber. They do not have this kind of property. Right? Now, in terms of fibers, now the isomer conductivity, there could be a range from like 0.11 up to like 0.3, like flax 344, a little bit cooler. But to us, this is not significant at all because a piece of fabric where we wear, typically 80% is the pore. Okay, there's 80% are porosity, pores inside. Only 20% are fibers. Now, when we talk about insulative material like down or like Thinsulate, that the porosity could be 99%. Okay, and only 1% are fiber. So whatever fiber you have, in terms of this kind of coat protective garments, that really doesn't count much. Okay. Now, those are the natural fiber materials or conventional fiber materials. Another very common thermoregulatory material for clothing is what we call phase-changing materials. Phase-changing material could be containing basically water or ice or paraffins or fatty acids. Right? It was originally invented by NASA, but being used in clothing. But generally, to have a relatively long-term effect, it has to be very heavy. Like this jacket, it's very bulky and heavy. It probably can only work for half an hour in terms of its effect. Another class of passive thermoregulative clothing we call the moisture management fabrics. So then the moisture management fabrics can be achieved by the fiber level or yarn level or fabric level. The fiber level, the popular, very well-known fiber is called Coolmax, which is achieved by engineering the cross-section of the fiber, making the cross-section non-circular and helps the wicking of the moisture. And it could be at the yarn level or could be at the fabric, like this particular fabric we call the branching structure, imitating the branching structure of the tree and promote a one-directional liquid transfer, so that we help the liquid or our sweat from the skin transmit through the outer surface for evaporative cooling. Sorry. Sorry. Okay. Another class of passive thermoregulative clothing is having the temperature or moisture responsive materials. This could be achieved by changing the structure of the a membrane in response to temperature, or making the pore open and close using the temperature sensitive polymer like p-nipan, this polymer, or like this work by MIT Media Lab. They have a double layer fabric with different kind of expansion when immersed in the moisture. And so one side expands more and the other side expands less, make the fabric bands or the flap bands open, making an opening for ventilation. We have recently been working on a skin-like directional flow fabric. So the property we want to achieve is like our skin. Our skin is a perfect fabric or clothing material because it allows the sweat come out but prevents the external liquid. So in this demonstration, you see this is a typical cotton fabric after treatment. And so simulating the sweat from underneath, the liquid will go through the material and to the hot surface and drop. And then if we supply external liquid, and this fabric is water repellent. Right? So this is another way of, you can say, moisture management. The directional liquid flow is basically achieved by the wearability gradients. In a lot of sports on the fabric, we simulate things like a sweating glands. Another way of thermal regulation is by clothing design. One way is trying to have lip structures that lift up the clothing, because normal clothing, the clothing is sitting on the shoulder because of the weight. And in this concept, we trying to have mesh fabrics in the chest and the back area, and then have a lip structure, so lift up the shirts a little bit. And so as the body moves, and so there will be air movement next to skin, and creates next to skin ventilation, or we call a chimney effect, right? And we can also have a laser cuts in the garments as the body moves. The garments openings open up and closes, and to increase the ventilation. Now, later on, you will hear in-depth talk about the thermal radiative materials from Professor Yi Cui of Stanford University. Now, without going into the mechanism, actually, we try to evaluate the effects. So we actually purchased the membrane, the polyethylene nanofibrous membrane, which is infrared transmissive and visible light opaque. And we made them into the shirts, and we compared with a cotton shirt, and we tested on the a mannequin, and we set the mannequin non-sweating, completely non-sweating, dry mannequin. And we conduct the experiment at 26 degrees Celsius and 50% relative humidity. And we set the mean skin temperature of the mannequin at 35 degrees. And then you can see indeed the this thermal radiative nanoporous PE should have about 10 watts more heat loss, okay, compared with the cotton shirt. So it is has more cooling effect. Now we also plot this. The heat increase the heat loss, okay, against the ambient temperature. So like when we did the experiment at 26 degrees, the additional increase the heat loss will be 10 watts. But also we plot the we call the predict the mean vote. Predict the mean vote is a measure of thermal comfort. So this value varies from -5 to 5. -5, which means extremely cold. 5 means very hot, okay? So when it's 0, which means for average person, it's comfortable, thermally comfort. So when you can see, if you're wearing a cotton shirt or this kind of shirts we're testing, it is about 27.5. That is 0. That the PMV 0, which means that is optimally comfortable. Okay, and then when it's really come to 29 degrees, it's 1, which means you're starting to feel a little bit warm. Okay, that but other, let's say if you look at a 29, 29.5 or 29 degree, you talk about 5 to 6 watts of increased cooling. Now, another class I call the active thermoregulative closing, which means I have external control on the thermoregulative closing. And one possibility is like this one you done is in the market, that by pumping air, so you're changing the thickness of the fabric and closing. Another way is, of course, electrical heating. And Dr. Boriskina already mentioned that even in 1939, right, people already thought about this idea.
And speaking of time, it's 10:36. So I just want to remind.
So, sorry, 1936. Yeah, okay.
No. It's now 10:36. So just keep timing in mind.
Oh, sorry about that. Yeah, okay, yeah. So actually, cooling is much more difficult. So there's one way is use fluid cooling, so liquid cooling, and in the middle of this picture is Apollo's liquid cooling garment. And on the right is electrical fan cooling. But with the liquid cooling, normally it needs a big pump like this, and so basically it's not portable. But the electrical fan cooling, you can see, really change the garment appearance. Now we have been working in this area also in collaboration of University of Boulder to have a thermoelectric cooling garment, but we just use the normal thermoelectric device, and we prefer to have that device in the concentrated area for convenience of heat rejection, and the air which is cooled by thermoelectric and channeled to the chest and back area, and we could achieve about 17 watts of cooling and heating in this system with the COP of 0.5. I'm talking about dry, completely dry cooling. There's no sweating condition, and in a sweating condition, slight sweating condition, you can easily go up to like 100 watts and much higher COP. Now in this work, we also better quantify the cooling required and heating required for expansion of the indoor environment by 4 degrees Fahrenheit, 2.2 degrees Celsius, which the Department of Energy used this to say that if we can have this expansion, we would be able to save about 15% of HVAC energy, which is a huge saving in energy. Yeah. So I have covered different kind of ideas we have for thermoregulation using closing, but each of them actually have an advantage and disadvantage. I only have suitable in limited application conditions. Yeah. So really, I'm looking forward to new ideas from the other two professors and also from the audience. Yeah. Thank you. Yeah.
Thank you very much, Jintu, for this great introduction to the field overall. And now we'll switch to the other two scientists of the future, who will speak in a little bit more detail about passive ways of thermoregulation, and then switching gears to active ways of thermoregulation. So Professor Tzu is next. You need to unmute.
Nice. Hey, well, thank you, Swata and also Gang for the invitation. Jintu just give you a really nice overview on the thermal issue of textile. Let me concentrate on just one That's radiation control. This is in collaboration with Shanghai Fan for a number of years now, using radiation on cooling and heating. And well, I think I want to acknowledge when we started this project, that was about 5 years ago, and ARPA-E has the Delta program, started by Ping Liu. Ping is now a professor at UC San Diego with Renkun there. It's trying to solve the building energy consumption issue, but change the temperature set point in your building. Summertime, you can allow it to go higher. Wintertime, you can allow it to go lower. You expand the temperature zone people can live in. Every 1 degree Celsius set point change, you save about 10% of energy used in air conditioning in building. So 2 degrees Celsius is 20, 30 degrees, roughly 30%. So it's a lot of saving. That was the starting point when we started this project. The question becomes, instead of doing cooling and heating the building, can you cool and heat individual? Then the thermal loss, and Jingtu just introduced, 1 person is about 100 watt of light, but under normal condition, not exercising condition, and radiate out the heat as one major mechanism, radiation, right? This heat loss has radiation, convection, evaporation. And below 30 degrees Celsius ambient temperature, radiation can contribute a lot. And once you start to exercise and body temperature, consume more energy, body temperature goes up, evaporation will pick up. And convection is kind of more static right there. This really depends on the local environment, whether you have airflow or not, and what's the porosity of your textile right there. So we focus on radiation in the indoor environment. That's one of the main heat loss mechanism. So using that, let's look at the radiation loss. Like human body, 37 degrees Celsius temperature, this yellow curve right here is really trying to show you the heat radiation, the wavelength of human body, center around about 8 to 10 micron, 8 to 11 micron also, from 4 to 20. So this is a mid-infrared wavelength range. Indeed, this is a very challenging range in terms of thinking about cooling. The reason is, in this wavelength range, we know the textile materials, you have this chemical bonding, like CO bond, OH bonding, and this bonding absorb in this wavelength range. This is a vibrational frequency of this chemical bonding, these molecules right there. So there's very few materials that could allow infrared, human body infrared radiation directly go out from skin, penetrating, transparent, make your textile transparent to this wavelength. Very few material except polyethylene, polypropylene type of material. Very simple bonding, carbon-carbon bond, carbon-hydrogen bond, and it only has very, small, I would say, absorption peaks right there. So this was my student, Po Chun Xu, starting this project, who is now an assistant professor at Duke University. And Po Chun was looking into this problem. So we were discussing, how do we utilize polyethylene and polypropylene for this purpose? So one big problem showing up is it's transparent to the visible light. Jingtu was telling everybody, right, the first function of textile, first invention of human being is cover the body. And visibly cover the body, not infrared, but visibly. How can we make this polyethylene to be opaque to the visible light? So we start to engineer nanopores in there, right? In a few hundred nanometer scale, they scatter visible wavelength of light, 400 to 700 nanometer. Now you see this white colored polyethylene. This is indeed, for the convenience, this is a battery separator. My lab has been doing battery for 15 years. So first time we measure this battery separator, we found out it's really, really cool. Allow the infrared transmittance, going out, right? If you put this side by side with, well, let's see, that's previous slide. And we have about 90% infrared transmittance. We can get to that level, but visibly it's white color, is already opaque. We measure this sample and compare with the bare skin, like in a fixed ambient temperature, with a fixed power mimicking the skin using this hot plate. Well, bare skin without wearing anything, 33.5 degrees Celsius. and nano P 34.3, a little bit higher, but will be a lot better than cotton, about 2.7 degrees Celsius cooler than cotton. So we were quite excited about this. It's a very clear cooling effect right there. But again, I think in Juntu's talk, Juntu was showing you already, if your ambient temperature goes up, your radiation, because environment also radiates towards you, this delta T between your skin and the environment is not big enough, and then your cooling power is actually reduced. So bear in mind, I mean, it's within a limited range of radiation cooling. It got to be below, 29, 30 degrees Celsius. But with this understanding, the first demonstration in the science paper is not available yet. It's non-woven, right? So we need to make it available. And Chan was a graduate student in the group. Is Jun Chen was a postdoc. Now Jun just joined UCLA faculty for about a year now. We need to figure out a way. How do we generate this nanoporous polyethylene in terms of fiber? And then you can weave or knit into a textile. So we develop a process of mixing oil with polyethylene and heat it up, and then extrude that out in a molten state, right? After you extrude this out, it cools back down, polyethylene becomes solid. And the oil is still maintained as oil, then extract out the oil. So we made this porous fiber, the spool of this fiber, and weave into these, really, weave into this textile that's about 2 meters long. So we were also excited this now turned into something we feel like more close to real, but still not quite there yet. There's a lot of tuning still needed. You need to pay attention to breathability, water wicking, and confidence level, and all this needs to be taken care of. So this is, for the industries to go take care of. But there's one more question we need to pay attention to. This porous textile, the scatter visible light, the white color. So we cannot get a whole world to wear white color, all become white, right? We need to offer different color. But if you use the dye molecules will absorb mid-IR, then your infrared transmittance will not be as good. We have to develop our own pigment, inorganic pigment, blend it in a small amount into a textile. This pigment, measure the infrared, mid-infrared transmittance, they're great. They don't absorb. For example, Prussian blue color, iron oxide, right? This gives you a reddish color, silicon, kind of yellowish color. Lily was a postdoc in the lab, joining UIUC as faculty for about a year. Also, really develop this color possibility, yet still maintaining a cooling performance, infrared transmittance. So I won't go into detail of that. So we have done extensive measurement. Then after getting the APAI's the support, right, we become more and more excited just going beyond indoor cooling. What about outdoor cooling? Outdoor cooling is different in the summertime. You have this sunlight energy so much, right? It's about 1,000 watts per meter square. A lot more energy than a human being can emit. We are talking about human, it's about orders of magnitude higher than humans' body radiation energy. So, and then you check the spectrum of solar. Solar, likely, nearly all the energy, they are below 4 micron. Human body starting to pick up radiation is about 4 micron. So if you could invent a textile, scatter back all the solar energy, but still allow human body energy to go out, right? That way you can do the cooling under the sun. The sky is really cold, so you can still radiate out. So now the thing is, how do we design this textile only scatter visible light and also near infrared? We put into this zinc oxide particle. You pick the right size, about a micron also. You can scatter the visible light near infrared, but not the mid infrared. The mid infrared still going out. Yeah, and with this design, we did a measurement, careful measurement of spectrum, and also mimicking the human body, using the artificial sun. This is a really big, compared to under the sun, the delta T, the type of cooling you can have is gigantic. So this is all good, and also warming will be the opposite, right? You need to block the infrared going out. You want to have low emissivity, and Svatas, you show this 1939, and this aluminum foil. Of course, aluminum foil would have will reflect the mid infrared. However, it's not breathable. What's needed is a really breathable and can reject infrared, but make sure it's breathable. So we have these nanoporous materials embedded into a textile, and also external surface needs to be low emissivity as well. And really demonstrated we have a really good warming effect. So I won't go into detail of all this data. And it's also possible by mentioning, you could do bifunctional, tuning the emissivity outer surface high or low by wearing this textile inside out. You could have a difference of a wearing experience. If environment temperature change, wearing your clothing inside out, you have a cooling mode and a heating mode could showing up. The delta T difference, through simulation we see can go up to about 9 degrees Celsius difference, and experimentally we show we can achieve 5 degrees Celsius difference right there. With all of this, there's so many ideas going to cooling and heating. You're going to hear from Renkun about active cooling, right? And also active heating as well if it's needed. And in this review paper in June, we kind of learn from the whole community, adding our own idea. We are writing this comprehensive review of thermal management and for the text. I encourage you to go read. So let me summarize. So I was showing you through radiation control, you can do cooling indoor, cooling outdoor, warming, and bifunctional, having cooling and warming integrated into the same textile. Let me also end my talk by thanking the DOE, ARPA-E, the Delta program to initiate this. I will look forward to the discussion with everybody. But one last minute, let me show you the real textile. This is the warming one, really thin. We already made into a product. It's going to be released next month, 1,000 pieces only, but limited version. And if you order that, you will have a card with my signature. Thank you. Well, thanking you for supporting early stage technology. We also have a cooling one already made right here. A testing, we have 1.8 degrees Celsius cooling under the mannequin testing. White color only, not ready to release yet, but by next summer, I will release another 1,000 pieces. And please support our early effort. Thank you very much for your attention. I'll stop right here and let Renkun take over.
Thank you very much. So you see, you can do a lot already without a battery, but you can do so much more if you do have a battery, and you can use active mechanisms of cooling and heating.
Absolutely. My batteries in the lab is already ready right there. High energy density.
Yeah, so Renkun, it's all yours.
Okay. Can you hear me well?
Yeah.
Let me try to hide this. Okay. Yeah, thanks Yi and Jintu for giving a very nice introduction on textile and radiative cooling. So that will make my job much easier. And we do need Yi's high energy density battery to power our device. So I will talk about active cooling and heating using thermoelectrics. I have a term called a rigorous approach in the title. I will explain to you later, but basically the idea is we use rigid thermoelectric materials but make them into a flexible form, as you can see in this photo. This is made by a fairly large collaborative effort, also supported by the Delta project at ARPA-E. The students working on this were Zhang, who is now in Illumina at San Diego, and Shan Mixin, who is now assistant professor at National University of Singapore, and also my collaborators, Sheng, Zhou, Shirley, and Ping from UCSD. So I will skip this couple of introduction slides, but basically we would like to have a personalized thermal envelopes for various reasons like safety, health, and thermal comfort. And as Jintu And he said it's relatively easier to create active heating, for example, just by geoheating, like in this heated jacket or this Climate A, at least from this company. And you probably have seen or actually used this heated electrical blanket. So I grew up in southern China, and at the time we didn't have AC or centralized heating in winter. It's actually very cold in southern part of China in winter. So I was very familiar with this electric blanket. So we already have this kind of personal thermal envelope we have been using. But as we know, cooling is much more challenging, as Jingtu and Yi just mentioned. There are actually quite a few products in the market already. So as you could imagine, you could use water, either forced convection or evaporative cooling from water. And you can also use a phase change material like wax to achieve active cooling. So this is a water jacket, and they also have a wax-based jacket from a company called Technic based in San Diego. I've talked to them. You can actually buy a prototype from Amazon. Actually, we do have one in our lab. So these jackets are actually very effective for cooling, as you could imagine. But there are a few disadvantages of using water or phase change material-based technologies. For one, they are very bulky, and sometimes they could be wet, so that's not very comfortable to use. And since they normally are based on phase change phenomena like vibration or solid liquid phase changing wax, so their temperature and heat flux are not very easy to control. And so what we would like to do is to use solid state active heating or cooling device. So the approach we are using is thermoelectrics, but this approach is not necessarily limited by thermoelectric. You can use other active cooling technologies, for example, electrocaloric effect. So the first thing we want to look at, does it make sense from a thermodynamic point of view? More specifically, if you want to achieve certain amount of cooling, how much power would you need? Because we are talking about portable variable cooling solutions. So we would like to have a small weight for our overall package. And this is where we actually need the high energy density battery, for example, from E. So we can look at some simple numbers from a thermodynamic point of view. So any active cooling or heating device is a heat pump. So it pumps the heat from cold side to hot side. It's like an air conditioner. And so we know there's a coefficient of performance. I think for most people in this audience, this is very familiar, like thermodynamic 101. So the COP is the cooling power you need divided by the power input, the electrical power input, the work you need to do for this heat pump. And of course, we are all bounded by Carnot COP. And so if you imagine we want to create 4 degrees Celsius of delta T, meaning we pump the heat from cold side of 33 degrees Celsius, is roughly the thermal comfort temperature on the skin, as mentioned by Jingtu. And also we want to pump heat to a hot outside environment like hot air, 37 degrees Celsius. And we have cold side temperature of 33 and convert to Kelvin and delta T of 4 Kelvin. And our Carnot COP actually is very high. It's about 80, or sometimes could be approaching 100. Unfortunately, now the device will actually work at a Carnot limit, obviously. So if we use thermoelectrics, there's a simplified equation to look at COP of thermoelectrics, and it's a fraction of the Carnot COP. And this ratio is determined by this ZT, which is the figure of merit of thermoelectric. And most of commercially available thermal device or materials have ZT slightly lower than 1 or close to 1. So if you put in ZT of 1, you will get this COP on the order of 10. So this is more or less an idealized scenario using ZT of 1 with thermoelectric materials. And so how does it compare to the other active cooling solution we just mentioned, like most commonly with water? We know water has a heat of fusion for melting about 90 watt-hour per kilogram. And for evaporation, it's about 600 watt-hour per kilogram. Now, let's say all these devices need to be, the thermoelectric device in particular, need to be powered by batteries. Let's say we use the best lithium-ion battery from E's group. And I guess this number, hopefully I quote the correct number, is about 200 to 300 watt-hour per kilogram in terms of the energy density of the, today's best battery. And so we can see that this number is comparable to the heat or evaporation of water if you can have a high COP, like greater than 1. So for example, if COP is 3, then you actually can get similar overall energy density compared to evaporated heat of water. And as we know, water actually is always one of the best and most common heat transfer fluids for a lot of heat transportation. So if you are operating similar to or better than water, you are actually in a good shape. And so obviously we like to have very high COP greater than 10, but this makes it possible using battery power thermoelectrics. So we think it kind of makes sense, but there are also other challenges, in particular heat transfer and mechanical challenge. So if you want to put a thermoelectric device onto our skin for cooling, if you look at more carefully, you are actually looking at two big problems. One is, this is what people have traditionally done in the past. If you have a thermoelectric device, you need to put it on the skin. And it's very bulky. And the main reason why it's very bulky is you actually need active heat sink, because you need to eventually dissipate heat from the hot side to the environment. But when the environment is very hot, like 37 degrees Celsius, you actually need this hot side to be at higher temperature than the environmental temperature. For example, 40 or even 40 Celsius. Then you also want to dissipate heat from the hot side to the environment. That's why most of the time you actually need active heat sink like a fan. And if you don't have a heat sink, then we are talking about natural convection and radiation heat transfer. These are the only two heat transfer modes from the hot side of the device to the air. And the combined heat transfer coefficient, HTC, of these two modes are at best around 10 or maybe 12, 15 watt per meter square Kelvin for natural convection and radiation. So that really make it really challenging to dissipate the heat without a bulky heat sink to the environment. So that's our goal. We want to make a sort of compact and less bulky thermoelectric device, meaning we want to get rid of this bulky heat sink. And also we want to make the device itself flexible. And our solution is we actually try many different approaches, including flexible thermoelectric materials like using polymers or organic, inorganic hybrids. But turns out those materials still have relatively low ZT, like less than 0.2 or 0.4. So they are not efficient enough. So what we eventually come up with is use this, we call a flexible architecture, but with rigid materials. So as you can see here, these pillars are N-type and P-type thermoelectric pillars. And they are embedded between two flexible layers, top and bottom layer. In our case, these layers are made of elastomers, and they are flexible and stretchable. And so in this case, even though individual pillars are rigid, they are not flexible, but we can actually bend and somewhat stretch this device as an overall device. And also, we want to match the heat transfer condition from the hot side, for example, on the top here to the air. So we actually create this device with specific design, thermal resistance between the hot side and cold side. We actually wanted to have a fairly insulative condition between the hot side and cold side. On the other hand, we also want to have heat spreading along the lateral direction within this elastomer, which is essentially a piece of polymer, but we want to increase the heat transfer laterally for better heat spreading. So these are the design conditions and goals. So this is a 3D schematic of the device we eventually made. And so in this case, we actually use air as a filler improve both the thermal insulation conditions between the hot side and cold side, as well as the mechanical flexibility. And again, you can see we have this elastomers at the top and bottom as the two layers to sandwich these N-type P-type pillars. And also these elastomers have enhanced thermal conductivity by embedding thermally conductive fillers like aluminum nitride, ceramic particles into this polymer. And again, here shows the regular thermoelectric pillars. And these are the photos of this design, this design thermoelectrics. And as you can see, they are flexible. I will not show all the details, but basically you can see the geometrical design of this device are very important. So here we can see this cooling effect. So this temperature goes down. So -12 means it's more cooling. As a function of G, here G is this parameter of the spacing between the pillar, like 3 millimeter. And then there's also H, which is height of this pillar. So for this particular design, we have a height of 5 millimeter and a spacing of 3 millimeter. So we can achieve a cooling effect around 7 degrees Celsius, the maximum cooling based on our simulation. And the reason is under this condition, we will have the thermal resistance of the device itself is about 0.03 meter square Kelvin per watt. And that's comparable to the thermal resistance of heat transfer coefficient to the air, which is about 0.1 meter square Kelvin per watt, or heat transfer coefficient of 10 watt per meter square Kelvin. And we can actually show the importance of this design. So for example, if you use commercially available off-the-shelf thermoelectric device, they typically have very high thermal conductance of the device itself because they are designed for cooling high power laser device, for example. And so this conductance is usually over 1,000 watt per meter square Kelvin. And our design typically have conductance around 30 to 40 watt per meter square Kelvin. And so you can see with our design, you can have much lower, much larger temperature drop or better cooling compared to the commercial ones. These are all based on simulation, and the material that we use are just commercially available thermoelectric material with CT around 0.8 to 1. And we can also see this exactly same device are also very good as an energy harvester for power generation from the skin temperature. I will not go into detail, but basically you can see in terms of the energy that you can harvest in terms of power density, units. This is much larger than what has been shown before. And the reason is exactly the same as I mentioned before. You need to have a good thermal design to dissipate the heat from the skin to the environment, even for power generation. And so as you can see here, that's because the peltic cooling effect and the seeback power generation effect obviously are correlated. So obviously you can see that when you put this device, when there's no heat input, you can see a large cooling effect, in this case from 25 to 18 degrees Celsius, about 7 to 8 degree cooling. And we can also put the device on a heater to simulate the heat flux from skin about 90 watt per meter square. And depending on the direction of the electrical current you're putting, when you turn on the current, in a few minutes, you can achieve a stable heating or cooling effect. And what is also important is for both the heating effect, which is showing as a positive temperature change here, and the cooling effect is showing as negative temperature change. You have this COP, so this blue curve showing showing the COP of this device for both heating and cooling. The COP could be greater than 3 for heating and will be greater than 1 for cooling. Under certain conditions, cooling COP can also be greater than 3. And this both heating and cooling as well as COP can be enhanced if you have a very mild like wind or forced convection condition. Again, this is also because of better heat transfer from the hot side of the device to the air. And we can show that the device actually is flexible. We can bend this for about 1,000 cycles with no much degradation. and the performance is the same when it's either flat or it's curved. And we did a small demo by integrating this device into a fabric and a coverlet on the arm. This is Zhang, the student's arm. And so you can see that we change air temperature from 22 to 36 degrees Celsius. So it's a wide range of air temperature. And without the TEC, so this part shows before the TEC is turned on, the skin temperature also changed, maybe from roughly 28 to 34 degrees Celsius. But of course, when you turn on the TEC, you can always achieve a target set point. In this case, the set point is 32 degrees Celsius. And this infrared image really shows when a device is cooling, the outside temperature, the hot side of the device actually is hot to dissipate the heat to the environment. And the hot side temperature is as high as 42 degrees Celsius. So you can dissipate heat from 42 degrees Celsius of the hot side to 36 degrees Celsius in the air. So when someone actually wears this device, they will feel cold, but probably you don't want to touch them because they're actually hot on the surface. And the other point I would like to mention is we show this as in the concept of thermal camouflage, where you can show the skin is invisible or blank from the environment in terms of thermal signature. But the real idea is we can embed phase change material like wax, these particles into our elastomer to create a heat sink. And the idea is, of course, we know the phase change material have a fixed melting point. As we mentioned earlier, for phase change material-based active cooling, it's difficult to control their temperature and heat flux. But we can utilize this thermoelectric to control the temperature and heat flux, but still use the thermoelectric, the phase change material as a heat sink. So you can essentially convert a fixed heat sink into an adjustable of tunable cooling device. So as you can see here, so we put this device on the arm, and the ambient temperature actually change for a wide range temperature from 20 to over 30 degrees Celsius. But the device can actually show the same temperature as the ambient temperature with a phase change material. So that shows the flexibility offered by the thermoelectric cooling and heating. So to summarize, we think it's possible to use high performance rigid inorganic thermoelectric material to create flexible thermoelectric device for cooling and heating. And the key is to design device. And there are many other aspects that we actually still need to work on to really make this device commercially viable. So from materials and device point of view, it's always good to have higher ZT, and we also want to have a better elastomer material that's soft and also with high thermal conductivity. And maybe we want to integrate it with textile, for example, EN Sintus textile for radiative cooling. And there are also possible alternative manufacturing process that will make this device much thinner and lighter. And we actually have talked to many companies for the past few months, and we've got a lot of sometimes surprising questions like, but the main aspect we need to focus on and we are working on is the performance and portability of the device and durability of the device as well as the cost. This is something we're still working on. So yeah, that's my introduction for the active cooling. Yeah, thank you for your attention.
Thank you very much, Renkun, and thank you all for great presentations covering all these different aspects of thermal management in textiles and wearables. And I would like to remind the audience that we are taking questions. You can ask any of the panelists, or you can ask the same question to all of the panelists. Okay, we seem to have a question for Renkun. How does moisture and sweat affect the thermoelectric performance of your devices?
So the question is how the moisture affects the performance. Yeah, that's a very good question because as you saw earlier, the device really utilizes air as a thermal insulating layer. And if you have a moisture, you might actually degrade the thermal insulation properties. And also moisture itself could, if the elastomer layers are not permeable to moisture, you actually block the sweating and vapor transfer, which is a very important mechanism for skin heat dissipation under wet and moisture condition. So there are ways to make this elastomer still porous and vapor permeable. And so as a result, you can actually have a vapor transport and sweating mechanism. But this porous elastomer layer needs to be still hydrophobic, so you don't really intrude the thermoelectric material. So there's something that we can still do to make device work under wet and moisture condition, but still more work to be done, I would say.
Thank you very much. So this was a question from Richard Zhang, and actually I was thinking of asking a similar question to all the panelists, because obviously perspiration will affect radiative cooling performance too, and other types of heat transfer. So would you like to add something to this discussion?
Swata, say the question again.
How would perspiration, moisture due to sweating, affect radiative cooling performance?
Oh.
Or overall the fabrics that you are developing?
Yeah, I think the very minor sweating will not affect that. But then once you get to a lot of sweat and whole clothing is already wet, that's different. I think it will start to affect radiation cooling. Well, for the obvious reason, water and the mid-IR, this absorbing right there, and the emissivity and this optical property can change, yeah. But minor sweat is fine, just not completely wet.
Yeah, my understanding would be, if I'm wrong, please correct me, is that when you have some sweating, then you have evaporative cooling, so your total heat loss would be much higher.
Yeah.
Condition. So your percentage of advantage because of radiative cooling will be relatively lower. Also, maybe as I hear from you that you still have the same amount of increased dry heat loss because of the radiative cooling. All right.
Yeah, I think Jintu, that's right. I mean, it will be once the sweat coming out, sweat is going to take over to dominate the cooling effect quickly, for sure. But the radiation channel by itself still there. Its effectors, how much power loss due to that will get affected a little bit minor. Sweat probably will not change that amount of power. However, the dissipating heat, because you generate so much, you already have sweat. That sweat will take over.
Right, thank you. We actually have a follow-up question from Richard Zhang, more like a comment, that the sweat could cause shorts and circuit degradation in thermoelectric cooling devices and other wearable electronics. And I think this question can be extended overall to washing too, so any time of interaction with moisture. So maybe Renkun, you can comment on this first, and then if anybody has to add, that would be great.
Oh yeah, sure. I think the poor sweat certainly could potentially short circuit or some would degrade the electronics. So we have thought about it and we have done some preliminary demonstration. So you basically could encapsulate the thermoelectric materials as well as all these electrodes and other electronic components. So hopefully that will mitigate this issue. Yeah, and also some of the questions we got from many companies are like, can we wash these devices? And we actually test preliminary test on this device, just putting in water. Again, if you do encapsulation well, I think that could be well mitigated. But certainly there are other aspects, for example, like soldering and adhesive between different components of the device that will that could degrade or even damage it under cycled washing or heating conditions. Yeah, so there are indeed some aspect that we still need to look at it. Yeah.
Okay, anybody else has a comment on what washing could potentially degrade in your fabric performance?
Well, I think, Smarta, the washing requirement is always there for
Oh, absolutely.
all the fabric. It's indeed not trivial. Even for our cooling or warming text, our Jing will know a lot more. You do a lot of this type of testing. Then you need to survive in a number of testing. Like let's say winter clothing, maybe you require less, 10, 15 times type of range. But summer one will require a lot more washing. It's not trivial. And for example, our polyethylene, I mean the washing, the machine washing, passing that, and then what's the temperature you can wash. This we will need to provide guideline down the road to the customers. And the warm washing, hot washing will create very different. It could potentially damaging your structure right there. And I also see the real clothing testing down the road. All the engineering, all the idea you do maybe need to modify to a certain way in order to survive in the real environment of either washing. There's also mechanical bracing as well. Those testing all require not trivial. I mean, I just showed 2 real textile right there, and we have to look into so many the ASTM standard testing, need to pass this one and that one. I was academia research. We need to be aware of all this.
Right. Well, I have a fresh idea for all of you. For the way how people actually do washing, because if there are new advanced materials that are desirable for certain reasons, maybe we should reconsider how they are treated, because it could be better for the clothes, could be better for people and for the environment too, because it's not just that clothes degrade, it's that a lot of microplastic is being released during the washing cycle. And that's a big concern from the environmental point of view right now, right?
Yeah, yes, completely.
I think he is right, because clothing textile material has so much requirement. Washability is one a big challenge for electronic textile. People talking so much, So people trying to integrate electronics into the textile materials for harvesting energy, for provide active controls, but how are you going to handle the washability? That's a big question. And so sometimes I tend to think maybe the electronics and the textile should be detachable. So when you want to wash it, you have to take the electronics away. But another issue I think he mentioned also very important is the breathability. The heat, when we talk about heat transfer in textile and fiber material, I found very, very difficult. It's working for so many years, I found it very difficult, more difficult perhaps, I want to say, that maybe other engineering fields of heat transfer, because the breathability issue. The moist transfer always coupled with the dry, heat transfer is always there. Yeah.
We actually have a question from the audience that relates to this. I'm not sure to whom it was intended, but all of you could answer. From Sunil Mehra. So the question is, will the fabric be tight on the skin or loose? So that would also have a big difference, right? If it's breathable or not, depending on what kind of contact it has with the skin.
I don't know what fabric the person who asked the question
I don't
is
know,
asking about.
Depending on what.
Right. Yeah. I think depending on application, sometimes you want to be very close to tight fit, like bodysuit next to the skin. Then your question would be, still you want to have a breathable material, keep the skin dry, let the sweat coming to the surface to evaporate. Because under whatever circumstance, you want a breathable fabric. People tend to forget that, like we are sitting here not doing anything, like we are not sweating. Actually, we do still lose moisture. And if you have a material which is impermeable to moisture, then you will very soon feel wet skin, extremely uncomfortable, right? And so when you're trying to wear a little bit away from the skin, a little bit loose fitting, then you have advantage of the air movement. We call them microclimate onto the clothing there. And actually the body movement, when you're trying to move, and then the microclimate changes, that also creates some kind of thermoregulation. You know, and if you can let the moisture air coming out, or if you want to trap the air there, you can generate insulation or help dissipating the heat. I think depending on what application, where you want to wear it. Yeah.
Yeah, maybe I add a little bit. For whether it's tightly fit or it's loosened, let's say for radiation, right? For good radiation, IR transparent, just radiation mechanism alone, the difference is small. However, Jintu just mentioned this microclimate environment. If you have a little bit of moisture, evaporation, sweat, and things gets very complex, there will be potential big difference coming out, whether it's tightly fit or is it's a little bit loose. And also, what's the breathability of your textile? Just imagine, like, just one scenario for thinking. When you have sweat coming out, if it's tightly fit, you have the wicking, the sweat can come to the clothing surface and then evaporate, take out the heat. If it's loosely wear, you just evaporate inside first. If you have good breathability, the vapor will go out. So the two processes different. Harder to tell which one will be better. It really depends on your textile.
There are also two industrial tests that cover both of these processes. So
yes,
there is sort of everything. Yeah.
Yeah.
So I'll give the last question to Renkun, because and maybe Jintu you can add too, because you work on active devices. So how much power the device is going to consume for a duration of 18 hours?
Yeah, that's a very good question that we got asked all the time, and it's very important. Yeah, so the overall metabolic heat from our body, is to mention, is maybe around 80 watt, but we probably don't need to cool down the entire skin. So we're probably looking at cooling of 20 to 30 watt with the coefficient for 3. So you are looking at the electric power need of maybe 10 to 30 watt. So then it really depends on the energy density of the battery. We are counting on E to invent the next greatest battery that will give us, but let's say 300 watt hour or 200 watt hour per kilogram. I hope that's the right number. So then probably are talking about, if you have 1 kilogram of battery, of course, that would be very heavy. You could power for 10 hours.
There could be 400 watt per kilogram of batteries coming. Yeah, it's already available. Yeah.
That's great. Yeah, so it'll be lighter and for longer duration. Yeah, so we are counting on you, I think.
With these the advanced battery, I think the thermoelectric idea is very, very promising. But the one we work with Professor Gan Chen's student, Long Gui, that thermoelectric system, our COP is lower. We say we only achieve 0.5 by using this conventional thermoelectrics. But our idea is to cool the air first and supply it to the body. And then, because then you can have increase the convective heat loss. Yeah. Also, we want to have the thermoelectric in one particular place, and then we don't want to get away with the heat rejection fan, the heat sink fan, because we want to reject the heat as far as possible. So actually, I have a question to Renkun, because you have a very thin material, flexible material, which is great, really nice, to wear to the body. But your heat is on the other side of the thin material, is a very high temperature. You're saying like a 42. That heat can transmit back to the body, right?
Oh,
You're
yeah,
not covering the whole body altogether. Yeah, how do you deal with that? Yeah,
absolutely. Yeah, so that's exactly why we need to create this design. So the thermal conductance of this entire device is very low. It's only 30 watt per meter square Kelvin. So it's like a thermal insulation to prevent this heat leakage from the hot side to the cold side. Yeah.
But what if there's a little wind? The heat's actually blowing to. You say one area you have a thermoelectric device.
Right.
It goes to nearby. There's no insulation, and then how about the heat transmit back to the body?
I think that would be a problem. Yes, you will have local hotspots where you have the thermal device. It's very hot. Yeah. Yeah.
Yeah, I just want to be respectful of people's time because it's 11:31. So I would like to thank all the presenters today, and everybody who would still have questions, please send them to us and they will answer the questions. This will be posted on YouTube, so you can watch if you missed part of this. And I would like to announce the speakers for the next webinar. And the topic of that will be on thermal materials for building walls and windows. So going away from the immediate environment to a little bit more remote environment, but still very important. And we'll have Jan Kosney, Elise Strobach, Lon Yi, and Leon Glickman speaking, moderating the discussion next time. And again, please send us your suggestions for future events. Sign up for the email list so we can keep you updated on what new exciting topics are coming up. And you can always access past events, videos, and question and answer sessions on the website. And thank you very much again, all the great panelists of today. It was a great discussion, and I hope everybody enjoyed it. Thank you.
Thank you so much.